This video corresponds with Lesson 8 of Unit 4A, teaching you how to complete the square. This is a process that we're going to use to solve quadratic equations that won't matter if the equation can be factored or not. Earlier in the unit, you learned how to solve equations that were kind of structured like these, but they had to be factorable. Completing the square is a strategy that you can use whether or not the equation and the expression can be factored or not. So, let's take a look here at some of these examples to figure out how we can use completing the square to solve for x. Taking a look at the first example, x squared plus 14x plus 24 equals 0. The first step that we're going to take in completing the square is we need our variables on one side of the equation, we need our constants on the other. So in this case, to do that, I'm going to move the 24 by subtraction, and we'll be x squared plus 14x equals negative 24. So that might look a little bizarre compared to what you learned earlier in the chapter, but if you're trying to solve solely by factoring, it has to be equal to 0 using a zero product property. Completing the square process, you're going to see this will look a little different, but in order to get it set up properly, variable terms on one side, regular numbers, your constants on the other. Now, the second step that we're going to take here is we're going to take a look here at this quote-unquote b term. Okay, so if you think of in terms of the original problem, it's an ax squared plus bx plus c order. The middle term that's with the regular x is that b term, the b coefficient, whatever you want to call it. I'm going to take a look at this number here, and I'm going to do two quick things to it. I'm going to take that number, cut it in half, then I'm going to square it. So if I take 14 and cut it in half, I get 7. If I take 7, then square it, I get 49. That 49, I'm going to add to both sides of the problem. And you'll see how this will work in just a second. I'm going to take that 49, add it to both sides. So again, we get that by taking the b value of 14, we cut it in half, get 7, squared, we get positive 49. If I add 49 to both sides, while that doesn't change the value of the problem because I'm adding the same thing left and right, it will change the look of it, which will allow us to solve it from here. So now, third step that we're going to take is I'm going to take a look at the left side here, this x squared plus 14x plus 49. That is a factorable trinomial. So I have to think what multiplies to 49 adds to 14. The only thing that does that, 7 and 7. Since I would have x plus 7 times x plus 7 and breaking that apart, could I write x plus 7 times x plus 7? Sure. But in terms of completing the square, I want you to recognize that x plus 7 times x plus 7 is the same as x plus 7 squared, because it's the same thing twice. On the right side, I'm going to combine like terms and get 25. This line right here should look very familiar to what you did in the previous lesson, solving equations by taking square roots. So from here, my goal is to get the x by itself. Now I can actually go somewhere and solve it. So I'm going to go ahead and take the square root of each side, because the square root will cancel out the square. I'm going to be left with x plus 7 equals, remember when I square root, that means there's a positive and negative root. Square root of 25, we know is 5. So I have x plus 7 equals positive or negative 5. We're going to go ahead and subtract 7. So we get negative 7 plus or minus 5 is equal to x. And again, since those are both integers, I can go ahead and combine my like terms. So I'll have negative 7 plus 5, negative 7 minus 5. And that'll give me my two final answers of negative 2 and negative 12. That's how you solve an equation by completing the square. It's the same process throughout all of these problems. So it's a little bit different. And in some of these cases, again, if it's a problem that could have been also factored, you'll get nice answers like you saw here in this problem. As you'll see in the next example, the whole point of completing the square is to allow problems that can't be factored to be solved somehow, some way. So let's go ahead and take a look at the second example here of x squared minus 4x plus 18 equals 42. Same steps we're going to take here. The first step is, again, variables on one side, regular numbers on the other. So I'm going to go ahead, subtract the 18, and I'll get x squared minus 4x equals 24. I'm now going to look at my b term. It's negative 4. So I'm going to take that term, cut it in half, then square it. Negative 4 cut in half is negative 2. If I square negative 2, it's a positive 4. One of the things about this second step here when it comes to completing the square, that number that I'm putting on both sides is always going to come out to a positive. It's the beauty of squaring numbers. Doesn't matter if it's positive or negative. When I square it, it's always going to give me a positive answer. So again, take that b term of negative 4, cut it in half, negative 2, square it, you get 4. We add 4 to each side. So now I look at the left side here. It's another factorable trinomial, x squared minus 4x plus 4. So the only way that can factor apart, what multiplies to 4 and adds to negative 4, would be negative 2 and negative 2. It's x minus 2 twice, so I'm going to say x minus 2 squared. Combine my terms on the right, I get 28. Now, we go ahead and start solving. So we're going to square root each side. We'll get x minus 2 equals plus or minus square root of 28. Now, square root of 28, we know is not going to come out really nice, but we're going to simplify it as much as we can. So, square root of 28 can break apart into square root of 4 and square root of 7, which means it's really the same thing as plus or minus 2 square root 7. My final step, add 2 to each side. I'll get x equals 2 plus or minus 2 square root 7. I can't combine that any further because I have an integer and an irrational number. That's as far as I can go. So that would be the solution there for that second problem. So it's the same process the whole way through. And with the last couple of examples I'm going to show you, we're going to still repeat the same process, but you're going to notice one tiny little difference. The difference in these last two examples compared to the first two, if you look at these last two examples here, the a value, so the number that's in front, is a number that's bigger than 1. It doesn't mean we can't do this, but there's one thing we're going to have to keep in mind in order to complete the square effectively. No matter what you have, if it's a number that's bigger than 1 out in the front of your problem. So if I look at the third example here, I've got this 5 that's out front. What I'm going to do is I'm going to take the whole problem and divide out the 5. Whole problem. Divide every term by 5 because I need it to be a regular x squared, no matter what. Sometimes it'll be a GCF when you take that front number out. Sometimes it won't. You'll see that in the last example here. It doesn't matter. You have to make sure it's a regular x squared. You divide by whatever number's out in front. So, if I divide everything by 5, I would end up with x squared plus 3x minus 6 equals 0. Now, from here, I'm going to go ahead and do the same steps. Once you do that initial step of making sure you have a regular x squared, a 1x squared out in front, we are going to go ahead and repeat the same process. So again, I'm going to get variables on one side, constants on the other. So I'll have x squared plus 3x equals 6. Now, when I do this next step here, you look at that b term in the middle, it's 3. So, with an odd number term, it's still going to be the same process here, but you're going to get some fractions. So, if I take 3 and cut it in half, I'd have 1.5, or 3 halves. I then take that and square it. If I take 3 halves and square it, you take the numerator and denominator, square both numbers. 3 halves squared is the same thing as 9 fourths, or 2.25. This is what I'm going to have on both sides. I'm going to go ahead and put 9 fourths on each side. So this isn't going to be the cleanest looking problem, but it's how we're going to have to work this through. So we're going to go ahead and keep solving from here. So if I factor this apart, now you're probably thinking, well, how do I figure out what multiplies to 9 fourths and adds to 3? Well, the nice little trick, if you notice from the last couple of problems, whenever you cut the b value in half, that's the value that ends up working this problem that you end up using twice. So if you go back to like the last couple of examples, if you look at the first one, when we cut the 14 in half and got 7, look what ended up in the factoring parentheses, 7. When we cut the negative 4 in half in the second example, we had negative 2. Look at what's in the parentheses, negative 2. You might get a gross fraction here and think, I have no idea how to break this apart. Well, we know how to cut 3 apart. It was 3 halves. Okay, we cut the 3 in half and got 3 halves. It's going to be x plus 3 halves squared equals, for the sake of putting this together accurately, I'm actually going to make this one big improper fraction. So 6 plus 9 fourths 6 is the same as 24 over 4 plus 9/4. I'm going to have 33 over 4. Use your calculator. If you're not so great at fraction math at this point, use your calculator to put that together. You know how to convert it on your graphing calculator by this point to an improper fraction. Use it to your advantage. Now, it's going to get a little bit easier from here, I hope. We're going to go ahead and do the same steps. It's all the same process. Don't freak out if you get fractions. It's not the end of the world. We're going to go ahead and take the square root of each side. So I'll have x plus 3/2 equals plus or minus the square root of 33 over 4. Now, keep in mind your properties of how the square root of fraction. Now, good news is this. It's not going to be some ridiculous rationalization mess. Here's why. If we look at our numerator is 33. The square root of 33 is not going to go anywhere. But if I look at my denominator, square root of 4, that's 2. So it becomes the square root of 33 over 2. No rationalization required. We can make this just at least a little bit easier from that perspective. The final step, subtract the 3/2. You get a final solution of negative 3 over 2 plus or minus the square root of 33 over 2. Now, theoretically, you could combine that even further as one big fraction. So actually, I'm going to back that up half a step here. Since they both have the same denominator, you can rewrite it where the numerators are combined. Your denominator is one and the same. You can write it like that. Honestly, with that many steps, if you have a problem like that, that first part that we got here is certainly close enough. It means the same thing, but you can't combine them together because they have the same denominator. So again, the only difference, there were two main differences in that problem. First part of it, being there was a number in front of the x squared that's bigger than 1. You have to divide it away no matter what. Second of it being we had an odd number as our b value, which meant we got some fractions, which meant we got to be real careful with the math that we have. Again, if you get a fraction, it does not mean you're doing it wrong. It just means you need to be even more careful than what you were before. So let's take a look at this last problem here. Last problem we got is 4x squared plus 12x equals 15. So this one's actually set up a bit nicer in that the variables are on one side, our constants on the other. But we still have a front value of 4. We're not allowed to have a front value of 4. It's got to be a regular x squared. Everything gets divided by 4. So I'm going to rewrite this problem as x squared plus 3x equals 15 over 4. Isn't nice. So I'll just leave this 15 over 4. Okay? So again, got to divide away whatever's in front of the x squared. Unless it's a 1, then you don't have to worry about that. Now, we're going to go ahead and do the same steps we were doing before. Notice what's even nicer about it, though, is we have another x squared plus 3x. So this should look oddly familiar to the last example. Take your b value, cut it in half, you get 3/2. Square 3/2, you get 9/4. So we'll have x squared plus 3x plus 9/4 equals 15/4 plus 9/4. So again, we're taking that b value, cut it in half, square it. That's how we get the 9/4. Now, we factor the left side. Again, what multiplies to 9/4 adds to 3. Again, the little trick is when you cut that 3 in half in the first place, it's the number that you need. Once again, it was 3/2. So since it occurred twice, x plus 3/2 squared. 15 over 4 plus 9 over 4, that's 24 over 4. You know what's nice about 24 over 4? It's 6. So that at least comes out to a much nicer number. So again, you're not great at your fraction math, use your calculator to help yourself out. Now we go ahead and finish off the process. So we're going to go ahead and square root each side. We'll get x plus 3/2 equals plus or minus square root 6. You can break down square root 6 all you want. It's not going to go anywhere. So we're going to leave that alone. Subtract away the 3/2. You get a final answer of x equals negative 3 over 2 plus or minus square root 6. So again, this whole process of completing the square, it allows you to break apart problems and solve problems that cannot be factored. If you look at the answers of most of these examples, you get all these square roots involved. Those are problems that are not going to factor apart very nicely. That's why this process exists, because everything can be solved for. You can find x, and no matter what combination of terms and problems you have. That's how you go ahead and use the process of completing the square.